We have looked at acyclic alkanes. Now we need to look at cyclic alkanes, which puts carbons in a ring. Hopefully you're going to start seeing a pattern that we're going to use consistently with every other functional group that we will talk about this semester. When we are looking at cyclic structures, we need to add cyclo in front of the parent name because that is telling us that the carbons are connected in a ring. So that is that one additional piece. Looking at our ring, each corner represents the carbon that is there. So we start 1, 2, 3, 4. There are 4 carbons. It's a square. 4 is represented by bute. Our suffix, because they're all single bonds, is ane. And because it's in a ring structure, we need to add cyclo in front of it as one word. Write them together. Cyclobutane is different than butane. Butane we would assume is a straight chain or an acyclic alkane. So here we have our butane, our straight chain. In order to go into its cyclic structure for 2 carbons to bond, we need to remove 2 of our hydrogens so that they can bond together, creating that cyclic structure. So the molecular formulas for cyclic alkane is going to have 2 less hydrogens than its acyclic version because we need to be able to close those carbons in that ring formation. Once we're able to identify the parent cyclic alkane, we then need to look for branches or substituents, just as we had done with our acyclic alkanes. Looking at our structure here, cyclics always take precedence over any acyclic branch. In this ring, we've got 5 carbons. It's that pentagram, so it becomes pent, like pentane. All single bonds tells us that it is an alkane, so we use the ane suffix. And then we do have a branch here. In this branch, we have 1, 2, 3 carbons. 3 carbons gives us prop, and because it is a branch, it's that propyl substituent. If there is only one substituent on a cyclic or a ring structure, you don't need to use a locant number because it's always going to be carbon number 1 because we can count wherever we want to start because it's cyclic. You can put a 1 if you want to, if you need that locant value to keep the process moving forward, like to keep it within your brain of how to do those. It's just not required. So this becomes propyl cyclopentane. As I had mentioned, if you want to put 1 in front of that to tell you where that propyl group is, you can. It's just not required when it's cyclic compounds. Now we're going to look at a cyclic structure that has 2 substituents on it. We have the same ring as we saw in the previous example. So it is cyclopent because it has 5 carbons in that ring. And it's an ane because it's all double bonds between those carbons in that ring. So we have that cyclopentane. Now we want to identify the substituents that are branched off of this cyclopentane. So we have 1, 2 different branches on this cyclopentane. Looking at this red one first, we have 1, 2 carbons. That means it's an ethyl group. On the other one, we have 1, 2, 3. 3 carbons gives us the propyl group. Because we have two substituents on the cyclic structure, we now need to provide the locant value for each of these branches. You want to be sure that the branches have the lowest number possible. So I'm going to start counting with the ethyl branch, and I want to put that ethyl branch with a value of 1. And I want to make sure the propyl has the next lowest potential value. So I'm going to count clockwise. 1, 2, 3, 4, 5. In this direction, my ethyl group is on carbon 1 and my propyl group is on carbon 3. So that gives me a sum value for my locants is 4. If I start with propyl as number 1, I'm going to count counterclockwise to make sure that the ethyl group has the next lowest potential locant value. 1, 2, 3, 4, 5. So this has me as the propyl group on carbon 1, my ethyl group on carbon 4 with a sum total, or carbon 3, and a sum total of 4. These groups are equidistant from each other. So when they're equidistant from each other, we then move to the alphabetical. E comes before P. So E is going to get the lowest locant number. Therefore, this will become 1 ethyl, 3 propyl, cyclopentane. I have accounted for all of my carbons, and the substituents are numbered with their branches. Once again, we have that base compound that we've been working with, cyclopentane. Now we need to go through and highlight our substituents. So I see that I have 2 single lines, and then I have another branch. Looking at the 2 single lines, because they only have 1 line or point, those are our methyls. So we have a dimethyl because there are 2. And then on our other branch, we've got 1, 2 carbons, so that is our ethyl. Now that we have our substituents identified, we need to give them locant values. Giving my numbering, starting with my ethyl, let's say that has locant value 1. That means my dimethyls need to have the lowest potential number, so that's going to be 2, 3, 4, 5. In this route, our ethyl has 1. Each methyl has 2, so that gives us a total sum of 5. On the outside, if I give my methyls 1, I'm going to count counterclockwise. 2, 3, 4, 5. So that means my methyl groups each get a value of 1, and my ethyl is a value of 2, giving me a total value of 4. That is the numbering system I want to use, even though the carbon numbering is technically equidistant. There are 3 groups. Each group would need to have been equidistant, but because we have 2 on 1 carbon, we have to use the total locant value. When in doubt, just make sure you sum up your numbers and then pick the lowest one. Now E comes before M, so E is going to be on carbon 2, so this is 2 ethyl. And then our methyls are on carbon 1, so 1, 1. I'm going to run out of room. Barely made it. Organic naming, I swear. All right, so then we get that 1, 1 dimethyl. We've got that 2 ethyl. So 2 ethyl, 1, 1 dimethyl cyclopentane.